After we finish with the
It's starting to look like, yeah. Well, I think you could probably drive it a bit higher and set the resolution. Yeah. Or maybe scale. Yeah. Go high. Better, maybe. That's good enough. All right. Welcome to the token binding work group at IETF94. Note the note well. We have a fairly short agenda today. We're actually going to flip the order of this a little bit and start with the token binding for HTTPS. The author couldn't make it here this time, so Vinod is going to proxy him, I think. So if you want to start, and remember to stand inside the pink box. See if we can find the other presentation. We're gonna slide you up, but do you want that too?
God knows how that's going to work.
I think you got to go put it in.
I'll put it in not a USB.
Yeah. Oh, thanks. Anybody need the blue sheet? All right. Yeah, here we are. Oh,
Forward, backward.
all right.
It's not in the slideshow. It's going to
Okay.
be, well, it would be amusing.
No, it's gonna auto flip. All right. Oh, do you have control, Vinod? All right.
It's hitting buttons and it's doing random stuff.
What more can you ask for, right? Now, I think you need to go full screen, right?
We can just go forward and hit the button.
Nothing happens? All right, you just have to tell us when to flip. All right.
All right. Good evening, everybody. Konnichiwa. For this session, we're going to be talking about token binding. Next slide, please. Just to give you a quick overview, I'm going to recap token binding for people who haven't encountered this before. We'll talk a little bit about the changes that have happened since the last meeting. And we'll get into a little bit of detail about the threat model that we're trying to address. Next slide, please. So let's start with sort of an overview. The key problem that we're trying to solve is the following. There are lots of services on the web where, for example, a user presents an ID and a password and gets a cookie or an OAuth token. And then the rest of the interaction between the user and the service uses that OAuth token or the cookie. And the problem is that if this cookie is actually stolen by some actor in the network, by one of a variety of mechanisms, a cross-site scripting attack, a network man-in-the-middle, malware on the machine, this actor can now can wield the cookie, can present this cookie and essentially steal the session. And what we're trying to do is throw cryptography at this problem and make it possible for the server to detect when this is happening so that we can deny the attacker that session. Next slide, please. Oh, sorry. So the key idea is what we're doing is we're adding kind of, sorry.
Sorry to interrupt, but do we need an extended recap this time? Or is there anything that we can, can you skip to the issues so that we can sort of get onto those? I think we...
Sure. Well, I see a lot of new faces, so we're hoping to do a quick recap. But
I encourage those people to read the draft.
Right, we actually have a very light agenda today and plenty of time, so
indulge the man then.
we're going to indulge, for a little bit because again we have plenty of time, so we're not going to be short on time.
All right. And so the key idea is that the client, essentially, we're creating infrastructure for a second factor. So in addition to the cookie that the browser presents to the server, it presents proof that it has the right to wield the cookie. And it does that by basically creating a key pair for use with that server. And to protect privacy, we use different keys for different servers. Obviously, we want to keep our private keys safe so that nobody else can use them. The client discloses the public key to the server, and then it proves to the server by signing a secret. In this case, it's the EKM, the exported keying material in the TLS handshake. It proves to the server that it owns the private key. And the result is that the server can say, oh, this is the client that is authorized to wield this particular token or cookie. Next slide, please. And so for example, when the user signs in, in addition to the user ID and password, we're sending this token binding header, which contains the token binding ID, and the details of that are in the token binding protocol spec. Next slide, please. And in this, so when the server mints the cookie, what it typically does is it takes this public key and puts some information corresponding to the public key, either the key itself or fingerprint of the key, or some information derived from it into the cookie. So that next time, next slide, please, when the cookie is presented to the server, it can confirm that this cookie matches the header that came along with it, which is tied to the TLS session. A lot of interactions on the web also take the form of federation, where you have a relying party asking, a user visiting a relying party that eventually redirects the authorization through an identity provider. So in this case, for example, the user goes to the relying party and says, I want to log in. The relying party redirects the browser to the IDP, and the IDP gets the user to log in if needed, and then issues a cookie issues a token that the client then presents to the relying party and gets a cookie. Next slide, please. And again. So by default, if we don't have explicit support for federation in the token binding protocol, the ID token that is issued by the identity provider will be bound to the identity provider. And next, please. And so when it is presented by the client to the relying party, there's no way for the relying party to actually verify that this token should be acceptable. And so what we really need is for the ID token to actually be bound to the relying party, so that the relying party can actually verify that the token is supposed to be used by the client. And in order to do that, when the identity provider issues the token, it should actually bind it to the relying party's token binding key not the identity provider's token binding key. Next slide, please. And we do this by allowing the relying party to signal the client to disclose its token binding ID to the identity provider when it goes through this redirect. So the presence of this new header, the include referred token binding header, tells the client that it's okay for it to disclose its token binding ID to the identity provider, so that the next stage of the protocol, the identity provider can actually issue a token that is bound to the relying party. And so the flow basically takes the form where the redirect happens, the relying party sends a message to the client saying, add your token binding ID, add the token binding ID that you use for me to the request that you send to the identity provider. And this token binding header now contains two pieces of information. It contains the token binding ID that the client would normally use for the identity provider, which is how the identity provider can verify that its interaction with the client is legit. Next slide, please. And it also contains a second token binding ID called the referred token binding ID, which is the token binding ID that the client would use with the relying party. So now when the identity provider issues the token, it actually binds it to the referred token binding ID, which is the token binding ID that the client would use with the relying party. And when it presents the token, next slide, please, it has the correct information in there. So now the client presents the IDP issued ID token to the relying party, and it has the correct information in there. So what changed from the previous meeting to this meeting? Basically, at the end of the last meeting, based on the discussion, we changed the name of the header from sec token binding head to token binding. The motivation still remains the same. We want that header to be protected and not be able to be manipulated by scripts and other, especially by scripts in the browser. But the name is now just token binding. The second big change that happened is we moved from using TLS unique as the secret between client and server on the TLS connection to using EKM, the exportable key material. Basically, the TLS unique didn't have enough randomness in it, and it was a little unsafe against some attacks. And then we updated the security considerations section of the spec, basically discussing two key items. Why do we want to disallow scripts from setting the token binding header? And why do we need to actually prove possession of two keys for federation? Next slide, please. So let's look quickly at the threat model that we're trying to solve here. The key assertion that token binding provides is the following. When the server verifies the public key signature in the token binding, it's actually getting proof that the client that's presenting this token binding header to it controls the private key. And this is an invariant that we want to maintain. And really what this proves is that what it makes possible for the server to tell is that if this invariant is ever broken, if the presenter of the cookie or the token is unable to prove that it owns the private key, something is wrong and it is able to deny the continuation of that session. Next slide, please. So there's basically two avenues of threat. One is an attacker uses a victim's private key, and the other is the attacker makes a victim use or essentially present a token binding header that uses attacker's public key. The idea essentially is that if the attacker can convince a client to use a header that it provides, the token that is issued will be bound to a private key held by the attacker, and the attacker will be able to continue the session based on that. Next slide, please. To protect the victim's private key, there's basically two key countermeasures. One, keep the private key a secret, and ideally we might want the private key to be backed in hardware, so it's actually not possible to be exfiltrated from the device. The second is we don't transmit it over the network. So if there's a man in the middle in the network, it'll never see the private key. Next slide, please. To prevent the attacker from being able to convince the client to use its token mining, to use its private key. I'm sorry, the question?
Yeah, generally the issue with a victim's private key is not that you actually get the private key, but that you somehow get the victim to sign something that you would like them to sign. That's how most of these attacks go.
Right. So if in our case, what we are signing is the EKM, and EKM is secret as part of the handshake itself. So hopefully that is not be violated.
Yeah, but you generally need some text around that you don't use that private key to sign other things which may look exactly like the EKM and stuff like that. It's just text in the security considerations. It's not that the protocol is bad. Just
Got it.
yeah, constantly is one way to get it.
So to prevent the attacker from essentially creating a header that the client presents, and making the client present a header created by the attacker, the first thing we need to do is make sure the EKM is secret. Because if the EKM isn't secret, then it makes it possible for someone who has access to the EKM to use their own keys to sign it and present it. Next slide. The second is we don't want an attacker to be able to set the token binding header. And the idea here is if, sorry.
I mean, I'm not saying it's bad for the EKM to be secret, and I'm not saying that it isn't secret, but why is it a problem if the EKM is not secret?
I'm sorry, again?
I said I'm not saying it's bad for the EKM to be secret. I'm not saying that it isn't secret, but why is it required for it to be secret? I don't see how. And bear in mind that we used to be using unique, and unique was not secret. Or not necessarily secret, at least.
Well, so the key idea is it's sort of one more layer of defense, right? Just it being public is not bad, but in combination, if for example 2 or 3 things fail at the same time, then it becomes an issue, right? If for example you can't export if the EKM is kept secret, then nobody has access to it, and there's no way they can actually generate the signature that is needed to make the protocol work break.
Okay. I mean, I guess. I mean, I certainly agree it's good for it to be secret, but what I'm concerned about is that if the logic of this protocol depends on it being secret, then I'd like to understand what the proof structure is, because that's not actually does not correspond to my threat model. So, I guess what I'd be interested in seeing would be a description of an attack that relied on the EK that I mean, if you imagine like having a proof of the protocol, right? And you say what conditions, including the EKM being public, have to obtain for the protocol to be broken? I'd be if you think this is an important security problem, I'd like to understand what it was.
Right. So basically, for the protocol to not work, the EKM has to be leaked, and a attacker has to be able to set the header, for example.
Right. Okay. And
this is particularly relevant, I think, in the federation case, I think, isn't it?
That is correct.
Because you can learn the your origin part, the bit that was intended for the IDP, typically, just by being the IDP. And if you're able to learn the other part in some fashion, you could.
I see. So to be clear, this is an artifact of not using a sec header. Is that correct? That if you use a sec header, so let me see if I can restate this. As I understand the situation is that if the EKM is leaked, then the attacker can at least, depending on timing, potentially impose their own sec header, their own header that imposes their identity in the protocol. So I ask then, why are you not using a sec header?
Because if we know about the header, we can simply make the second condition true without having a sec prefix.
Well, imagine there was imagine you have a browser that does not support token binding, and therefore is not aware of the sec header, but it has for some reason allows you to extract the EK to operate an exporter on the TLS connection. Then under those circumstances, now I guess you're going to say that then I can't produce the right extensions in the client hello to negotiate token binding. But it seems like because the sec headers by default make it impossible to inject, then why would you not use a sec header? I mean, I don't think this is a huge deal, but I'm just trying to understand like what's the argument for not using a sec header? Given that you identified a potential vulnerability here. Okay, great. I don't think this is a big deal. Open to being, maybe it is a big deal. I haven't thought it through because I just heard about it 10 minutes ago, but I'm open to being convinced, but it just.
And finally, the third countermeasure is for the protocol to work, we want to make sure whenever the token binding header is presented to a server, it always verifies that the client can prove possession of every key that's in that header. And the idea here is we do not want, for example, a network man in the middle to be able to tack on things into the header that point at keys that are in control of that attacker. So the end result of this essentially is that whenever a server sees a token binding header, it can confirm that the client actually owns the private keys of every token binding ID that is in that header. Next slide, please. So I think, yeah, so this is kind of pretty much where we are at the end of the revisions after the last meeting and based on discussions that we've had in the working group.
So Vinod and Ecker, we actually went back and reviewed the notes from last meeting, and there was actually a discussion about the sec header. The consensus was that even though we could, the working group couldn't see a huge use for it, it wasn't seen as a bad idea, right? So why not just add it? I think was actually the conclusion from last meeting, and it would, and the group also called for some sort of threat analysis to be included in the document. Right. So I think those are. Can you say again, Ecker?
Yes, the word analysis is very useful.
Right, and we already concluded last time that we wanted that, and that having a sec, using the sec prefix might not be critical, but it wasn't sort of. It was seen as good hygiene.
Right. So then I guess you're putting the sec back in the sec in the header.
Right. So that's what the notes say anyway. So. All right. Anybody else? I'm curious to figure out whether how close you guys think this is to last call.
So I think we're pretty much converging on that. We've implemented 2 versions of this, and I think we're pretty much at that point.
So Martin Thompson, over the past, I think, couple of months, we've seen a number of interesting things come up in this sort of general area that may be of interest to people. And I refer here to the duplicate signature attack that was found on the Acme protocol, the proposal that was made there, and some of the unknown key share stuff that's happening as a result of the sort of analyses of TLS that are going on. I sort of wonder whether it was possible, if anyone had considered doing a formal analysis of this protocol, using whatever tools are available to sort of prove that sort of thing out, because I'm not entirely confident that we don't, for instance, have this duplicate signature attack in one form or other, particularly when we start talking about the federated case where it starts getting a little bit more vulnerable. I think, I don't know if it's unreasonable, but having that as a precondition for working group last call would make me a whole lot more confident about this. That said, I know how much effort that is, and I'm not necessarily going to hold anyone to a standard higher than I would expect of myself. So I completely understand if no one's willing to put up the resources for that. But that's something that concerns me greatly about this.
I think you're not volunteering. Or...
I've had a look at this Tamarin thing, and it's, I don't know where the square brackets go. It's weird. Ecker's had a look as well. He's got a better handle on these things than I do.
Andrei Popov. So to answer the question that the chairs asked about the degree that the authors believe this is ready, I believe this is approaching, this is converging pretty well. And Microsoft has an implementation of this, Google has an implementation of this. We are pretty close to, actually at Microsoft, we're pretty close to enabling this by default in the browser. So we believe it's pretty good. With regard to security analysis, we have a team working on that. I don't know if they're using what specific analysis tools they're using, but there's definitely security researchers looking into the security of this, because it will be enabled by default again at some point.
So just to follow up on that, would any of you guys be willing to produce some sort of implementation report?
Well, definitely, yeah, I think we can do that, yes, we can produce a report. The next step for us would be to actually enable it and see how it fares out there in the wild. How deployable it is in practice. That's the interesting part.
And just for the record, for the working group, we actually, the chairs have actually requested early allocation of some of the code points from Mariana. And I'm not exactly sure where we are with that process, but given that you're saying this is, you guys feel that this should be close to working group class WLGC, maybe we're gonna overtake. We may not sort of have an early allocation before we're actually done, right? But so I'm just trying, because the list has been fairly quiet, right, over the last couple of months. I'm trying to figure out whether that means that everybody's happy or whether nobody's reviewing this, right? I mean, the fact that there are implementations is certainly a good indication that people are actually more or less like what they see. I mean, we saw one issue sort of being resolved today, I guess, on the list, but I would like us to come to a point where we can sort of, well, get done.
Right. And an early allocation would really help us.
Right.
Yeah, so one thing that I think actually is important is to be, I mean, so first of all, I think Martin's totally right. It'd be great to have, ProVera for a Tamarind model, though it is hard to do. It's a lot of work, and getting and understanding and really modeling the protocol accurately is incredibly hard. I would certainly be happy to read one if someone produced one. I might even be happy to have some drinks and try to write one. But it's one thing I think that would make me more comfortable is, I guess, is to have it be incredibly sharp that this is a belt and suspenders mechanism. Namely, as I understand it, the fundamental assumption is that you're authenticating with a bearer token, i.e. a cookie, and this is about making it not possible to move the cookie around. And so if this mechanism completely fails, then you fall back effectively, and that we're assuming you're doing TLS anyway, and we're assuming you're verifying the certificate. So even total failure of this mechanism should not need to compromise the world. Maybe it's purely a matter of writing that text in the document, but that's certainly, I'd be more antsy about this if I thought people were using it for primary authentication rather than for secondary authentication.
Yes, clearly this is a way to secure the tokens that result from the primary authentication. So this is not the authentication itself.
The only reason I mention that is, because you could use it that way, right? And you technically could, the protocol mechanics would allow you to do that, I think. Yeah.
I don't think we're at all prepared to deal with the possibility that something like this might happen in the clear, for instance, because then the binding between various things is. But yeah, a total compromise would probably, loss of, say, the private key of a client would probably not be the end of this.
No, I guess what I mean to say, yeah, that's what I mean to say is, imagine, we're just getting in the weeds a little bit, but imagine you had a mechanism where the public key was, where the server gets a binding the public key to the identity, or where the cookies were not inherently secret. Then you have a different situation. But I mean, protocol mechanics should be the same. But I think, so I guess I'm just suggesting that perhaps that should be made very clear in the specification if it's not already, which I'm not sure it is.
That's right. So basically, if there were a vulnerability and the protocol actually failed, all it does is it brings you back to where we are right now, where the cookie can actually be moved from one machine to a different machine and wielded. And really what this protocol is doing is it's aimed at preventing that.
All right, nobody else? I guess then, Andre, if you want to come up, and so you decided you didn't need slides, so you're just going to talk about the diff in the document. Okay. Now you're asking us to fiddle with the slides again. It's just...
Okay, my name is Andrei Popov. I'm with Microsoft, and I will talk about the changes that were made in the token binding negotiation draft and in the token binding protocol draft since the previous IETF meeting. So we're starting with the negotiation draft. Basically, you know, to give a broad overview, the two main changes that were made in this time frame. One of them was based on the feedback that we received in Prague, which was that we wanted to have an actual token binding protocol version negotiation rather than token binding protocol indication. So previously what we were doing was, you know, the client was indicating in the TLS extension the token binding version that the client supported, and the server either echoed that and then we had token binding going on, or the server just, the connection continued without token binding. The server would not echo the version that the client offered. This, you know, we decided that that was not expressive enough, that we wanted some kind of negotiation. So in this version, I'm introducing a TLS style negotiation where the client offers the highest version of the token binding protocol that the client supports, and then the server responds with the lower of the client supported and server supported versions. And we'll see that in this draft. If we can scroll down to some substantive changes, you will see that the text has been changed to do exactly that. So the client offers the highest version the client supports, and the server echoes that, and then the server responds with the lower of the client supported version and the server supported version. This is how TLS version negotiation works. It's a fairly simple mechanism. That's what we've introduced here. Yeah, it's great if it's a little bit larger so people can read. That's the one large change that happened. The other significant change that we introduced, if we scroll down a little bit further, okay, so here it talks about the fact that if the client does not, if the client does not support the token binding protocol version that the server has returned, then what happens is basically we proceed without token binding. So we're not breaking the connection because of that. Yes. So and if we move further down, so this is we'll see probably the next change that was made, which is we switched from the use of the TLS unique to the extracted key material from the TLS session. There was a discussion, there was a thread on the mailing list where we decided the TLS unique was not secure enough. It's few bytes. It could in principle be replicated. So a man in the middle could in principle produce a session with the client and the server that have the same TLS unique, and that would break token binding. So instead of TLS unique, in this version, we're using extracted keying material from the TLS session. In the token binding protocol draft, there is text that describes exactly how what parameters are passed to the keying material exporters. So this change actually has simplified the message formats, and we'll see that as we go on. Yes. So if we could scroll down further. Yeah, everything else. Yeah. Now we can switch to the next version. So once we made the previous changes, we also looked at our here. Please stop here. So we looked at our token binding key parameters IDs, and we found that we no longer need the hash suffixes on them because the extended keying material is the value that we directly sign. So we don't need to hash anymore. So we don't need to negotiate the hash function.
Yes. I don't in principle have a problem with that. May I ask what appears in the digest info in the PKCS15 signature?
In the PKCS
the PKCS15 variant,
right.
What appears in the digest info field? Well, I mean, there's a thing, right, that goes in the
yes, the actual KM value is what we.
Sorry, no, but okay,
but
typically aren't PKCS15 signatures,
right?
They're ASM1 encoded, right?
Right.
So what goes in the algorithm ID field for that? If you're not using a hash.
Not using a hash.
I mean, I'd be happy to strike 1.5 entirely.
I see what you mean.
Is there a reason
I see what you mean.
I mean, maybe that's a different question. Why should we have 1.5 here at all?
The only reason we have 1.5 here is that this is the only type of padding that TPM currently supports.
I see.
So for use with TPM, if we want to bind the token binding key, if we want to store it in the TPM basically, then that's what we have to use. That's the only reason for that.
Okay, so I think this may need a little more specification.
Yes, I see your question. We'll clarify that.
Okay, and for PSS, you also need to specify, I think, I didn't see the name of the algorithms used for the salt generation.
Right.
Stuff like
right.
That.
I'll specify.
So I think it's great. I think it's perfectly fine to tie the digest algorithms in some fixed way. I just think you may need to be a little more explicit in the text.
Right. So this is the change, and if we scroll down, I don't think there's much else that came in this revision.
I also have one point that I just wanted to make earlier.
This is sort of a trivial point, but it might merit some discussion. In the introduction, in the client text that describes generating the extension, it says that you're supposed to list the parameters in descending order of preference.
Right.
And in the server text for processing the extension, it says you're supposed to pick the one you like best that's in the client list.
Right.
And so those seem to not have much to do with each other. And that seems to tell the server to ignore the client's order.
Yes.
And so I suggest that you remove one of those two statements.
Well, the reason the both statements are there, I mean, this is the way actually TLS works as well. The client offers cipher suites in the client's order of preference, and the server is free to listen to that or not, right? So
But the server in TLS, the TLS server the specification is agnostic about the server's algorithm, and here you propose a server algorithm.
Right. Here I recommend. I'm saying should. Yes.
Right.
But in principle, you could imagine a server that honors the client's preference.
Sure.
As a non-default mode. That's what I was thinking about. So it's useful. Like, I think it's more useful for the client to offer some kind of ordering than to offer no ordering. Okay. Because it could in principle be used, although that to me the server should be driving this. That's why I'm saying should.
I can certainly live with this. It was only I only bothered to mention it here because I thought it might merit some discussion rather than just
By the way, we do the same in LPM. Another one, yeah. Yep, and that's it with the spec. And then now let's look at the practical. Okay, so in the protocol spec, we see the same changes echoed. So we're using exported keying material instead of TLS unique. Down, please. Okay, so this is just, yeah, better references. Let's move on. Okay, so in the actual message formats, we were able to simplify the message formats now. So what I'm doing here is in the token binding message, I'm using the same token binding key parameter IDs that we have negotiated in the TLS extension. So we don't need to have the hash algorithm structures from TLS again. So that basically simplified the structure of our messages. A little bit down further. So that was a simplification, basically, to use the same algorithm IDs throughout the token binding protocol.
Just a small error, I think. These have hashes on them.
The next spec, this is not the latest version. This is the previous. Unfortunately, I have no way to diff all the way through.
Yes, you can.
Can I?
You can type in the URL 1 equals draft IETF TOKBIND protocol base version.
Okay. There's a better way.
And then we can see it all at once.
Thanks, Martin. That's a good suggestion. Yeah. No, 3 and 1. Yeah. He wants to get it.
Oh, no, euro 1 and euro 2. Yeah, and euro 2 needs to be 1. Change euro 3 to euro 2.
I think so, yes. Yep. So let's go back to that same spot. Yes, so now the IDs are without hash suffixes. So this basically helped us eliminate a number of structures from the message, which is always a good thing. That's what we've got here. Also, we figured out that since the elliptic curve is already part of the key parameters, we can just use EC point structure directly. We don't need to put the same information in two places in the message. So this was another simplification that we made, and let's scroll down a little bit. So this section talks about specifically what parameters we're supplying to the key material exporters. So there is a label, exporter token binding. It's prefixed with the string exporter to avoid collisions. The application context data is null in our case, and the length of the key material that we're exporting is 30 bytes. At the previous meeting, we had a comment asking us to provide some explanation of why we need extensions, and I'm giving an example use of extension of an extension of the token binding protocol, which is to provide attestation, to provide a way for the server to confirm that the client actually secures the key in a hardware module. So for that purpose, we're planning eventually to develop an attestation extension for this. We're not ready to specify it right now, but we're leaving this extensibility point in the protocol for future use. Scroll down, please. So this is more of the same. Basically, again, the simplification of the token binding ID structure, the same as above. We can scroll further. Yeah, so this is basically all of the interesting changes in this draft. So to recap again, two big changes. One is the negotiation of the token binding protocol version using TLS style kind of negotiation. And secondly, the use of extended key material instead of the TLS unique. Any questions about the drafts? Any questions about the changes that we made?
I haven't thought this through, so I'll just put it out there. In TLS, we've been moving towards having signatures have a context string associated with them that is fed in. I think so you look at the 1.3 signatures, says, TLS, blah, blah. I think that the exporter does that job, but unless you think it doesn't, I just wanted to raise it in case you thought it didn't do that job. It's hard for you, given that you're going to hash the data anyway, it's hard for me to understand how it helps to, to hash the string exporter in and then hash some extra string on the outside. But I just wanted to raise that in case anybody thought that I was out to lunch and we need to have a separate context string. Otherwise, this looks pretty sound. Except for the fact that session hash is now in RC. Oh, you did?
I'm hoping this is an indication that people are, more or less fine with the drafts, right? Can I ask a question? Who here has read the last version? Yeah. Who here has read any of the versions? Okay. a relatively recent version, right? I would like to get a few people on the record promising to do like a review on the list, because I think we need to do that, and then we can sort of demonstrate that we've gotten good enough review so we can actually start to sort of move towards. Yoav, are you volunteering? Yeah, okay. Martin, Yoav, Jeff, Tony, and Ecker. Can you put just put that in the notes, because we're going to hold you to it, and just sort of post something on the list. I'm going to go ahead and say any kind of review is good, but the more thorough, obviously, the better. And you're probably going to revise one more time after that, likely, yes. Right?
Yep.
But I think that after that, we should be thinking about working group loss call, I think.
Sounds good.
Yeah.
Thanks.
All right. We're at open mic time, and as I said, we did plan for a lot of extra time here. So, issues, questions, comments? All right. In that case, you're going to get an hour back, I think. Thank you. Blue sheet forward, please.